Hi, this is Pankaj Jairu. I am doing this video to solve a question, actually an imaginary question based on electric field of a charge, an electric field between two charges. Alright, so I'm given a condition where I have two rings of radius 2 centimeters. Means they're both gonna have the same radius. So I'm gonna make two rings right there. Since the radius is equal, I want to make them look alike. So there we go, and they have the same radius and they are like a certain distance apart, like from this here to here. They have a distance of let's say 20 centimeters. So this is 20 centimeters, and the question is asking us to find the distance, electric field at a distance midway between them. So right there, this is the line that divides the distance between the rings into two equal halves. So I'm given the radius of both the concentric rings, so which is 2 centimeters. So that's gonna be 0.02 meters, actually 102 meters. Then I have the distance between those two concentric circles, which is d equals to 0.2 20 centimeters. So which is actually gonna be 0.2 meters, 0.2 meters. And then I want to find this distance from right here to right there. So this distance, which is the distance from the center of the circle to the midpoint, which is gonna be the half of the whole distance. So the distance we need, d dash, would be 0.2 over 2, so which is gonna be 0.1 meters. So now, and the charge, we're given charge for both of the rings, which is charge equals to 35 nanocoulombs. So if we convert it into SI system, it's gonna be 35 times 10 to the negative 9 coulombs. So that's our charge. So for a general concept, we have the electric field, the formula of the electric field to be, so at a point G from the charge Q, which is let's say G right here, G is the distance between this point and this point, which is we don't know, we have to calculate it, and in this case it's gonna be 0.1 meters, yeah, which is gonna be the electric field equals to 1 over 4 pi epsilon naught qz over r square plus z square to the power 3 over 2. So we're gonna find the electric field at this point due to circle this one, and electric field at this point due to circle this one. Let's say this is circle A and this is circle B. So our next step would be to find electric field at G, at the point at the distance G due to A. So if we find it, then it's gonna be, so then we want to find the electric field at a distance Z due to A, which is going to be 1 over 4 pi epsilon naught times the charge, which is 35 nanocoulomb, times G, which is the distance of the point from the charge on A, divided by 0.02 squared plus 0.1 squared to the power 3 by 2. So what I did here is just plugged in the values of R, G and Q, so which came out to be, after a calculation, 2.97 times 10 to the negative 10 to the 4 and Newton per coulomb, which is the unit of the electric field. Again, we want to find the electric field on G due to charge at B. So we're gonna use the same formula, just plug in the values of the one at B. So I'm just gonna plug in the values and show what's the result are. So what I just did is plugged in the values in the same equation for the ring B, and what I got is we have everything the same. The charge on B is the same as the charge on A. The distance of G from B is same as the distance from G from A, and then I plugged in the charge, which is the same, and then I got the value, which is 2.97 into 10 to the negative 10 to the 4 10 to the 4. Let it look pretty. Yeah, Newton per coulomb. Now there is a question to think. Since these are in the same axis, if we suppose this axis to be x-axis, then if we want to find the direction of magnetic field on G due to A, then it's gonna be in the positive x-axis. Similarly, for x, it's gonna be, if we take it this direction, then it's gonna be negative x-axis. So this value is gonna be negative. So there is the deal. Now I'm just gonna create a new space right here. Now we can see the total electric field at a distance Z is gonna be equals to the sum of electric fields at A and the electric field at B. So these are two vectors, and since they two are the same, since we can see from here, this is the same value, this is the same value I can see over here. Oh, sorry. This is the same value again. So basically I'm gonna get the same equal values but in negative, so it's gonna be 0. So from this we can conclude that the electric field due to two equal charges at a distance midpoint between them is equals to 0. Well, this completes my question. Thank you, Dr. Red Allen, for watching this video. Thank you very much.